Hello everyone, welcome to this lecture series on linear algebra. This is fourth lecture and today we are going to talk about system of linear equations. So we are in particular going to see whether the system is consistent or inconsistent, and by consistency means whether there is a solution or not, and if there is a solution, what type of solution. And there is a theorem, Rouche-Frobenius theorem, which also talks about the consistency of the system of equations based on the rank. Okay, so let us first uh, take the definition that what we mean by a linear system of equations. Okay, so system of linear equations. Okay, so a system of m equations in n unknowns, where unknowns are say x1, x2, x3, so on xn. Okay, is a set of equations of the form this. Okay, so they are m number of equations and there are n variables x1, x2, xn, which are unknown variables, and a11, a12, a1n, a21, a22, a2n, so on. They are coefficients on the left hand side and they are numbers. Okay, similarly b1, b2, bm, they are also numbers. Okay, so where aij with the I varying from 1 to n and j varying from 1 to n, so all these a1, 1 to amn, they are numbers called coefficients of system, and the right hand side bi's with I1 to m are also given known numbers. Okay, so basically we have m number of equations and we have a system of m equations in n unknowns x1, x2, xn. Okay, so this system is a linear system of equations because the unknown variables are not multiplied together, or they are not in power, or there is no trigonometric exponential terms on the unknown variables. Okay, so if the right hand side numbers are all zero, okay, then this system is called a homogeneous system. Okay, so if all bi's, okay, so if this b1, b2, bm, they are all zero on the right hand side, then this system we call as a homogeneous system. And if any one of the bi is non-zero, then the system is called non-homogeneous system. Okay, so if at least one bi is not zero, then the system is called non-homogeneous system. Okay, now about the solution of this system. By solution we mean to calculate the value of the unknown variables x1, x2, xn. So a solution of system is a set of numbers x1, x2, so on xn that satisfies all the equations, all the m equations. Okay, so there are two fundamental questions about the linear system. Okay, and the first question is whether the system is consistent. That is, does at least one solution exist? Okay, so consistency simply means whether there is a solution or not. Okay, so if there is at least one solution, we say system is consistent. If there is no solution, that means no set of numbers x1, x2, xn satisfies all the equations, then system is inconsistent. Okay, or there is no solution. And the second question is that if there is at least one solution, okay, then whether that one solution is unique or not. Okay, if a solution exists, is it the only one, that is the solution unique? Okay, so whether there is a unique solution to the system, okay, only one set of numbers x1, x2, xn satisfies this, or there are infinite many solutions, so infinite many sets of numbers satisfies these m equations. Okay, so we are going to take care of these two questions today, whether the system is consistent or not, and if it is consistent, then whether it has a unique one solution or it has infinite many solutions. Okay, so first we see how the solutions look like. So geometric interpretation of the existence and uniqueness of a solution. Okay, so we are going to take example of two variables here. Okay, two variables in two equations. Okay, so if m and n are both equal to 2, that means there are two equations, and n equal to 2 means there are two unknown numbers x1, x2. So we have two equations in two unknowns x1, x2. Say these are the two equations. So there is a linear system of equations with one equation a11x1 plus a12x2 equal to b1, where a11, a12 and b1 are numbers and x1, x2 are unknowns. Okay, and similarly the second equation a21x1 plus a22x2 equals b2. So again a21, a22 and b2, they are numbers, and x1, x2 are unknowns. So uh, whether the system uh, is consistent or not, and if consistent, whether the solution will be unique or not. Okay, so there are only two variables, x1, x2, so we can interpret this result by seeing x1, x2 as coordinates in the xy plane. Okay, then each of the two equations represent a straight line. So you can see that this equation, you can interpret it as the straight line. Okay, and similarly this second equation also represents a straight line in the xy plane. So any tuple x1, x2 is a solution if and only if the point P with coordinates x1, x2 lies on both the lines. Okay, so basically the point x1, x2, if it satisfies first equation as well as second equation, then we say that this x1, x2 is a solution to this system. Okay, so any set of numbers x1 and x2 which will satisfy both the equations will be a solution. Okay, so there are three possible cases here. Okay, uh, for precisely one solution or unique solution, which is possible if these two straight lines intersect at a unique point. Okay, so then in that case we will have only one unique solution. Okay, or if there are these are two straight lines, if they overlap, okay, from one end to another and the whole line coincides, then we will have infinite many solutions. All the points on the line will satisfy both equations. Okay, and in case that these two lines are parallel, so they will not meet at any point, and so we will have no solutions. Okay, so no solution if lines are parallel. Okay, for example, say if you have two sets of equations where these a11, a12, b1, I have given them as numbers. So if you have one straight line as x1 plus x2 equal to 1, so this green line, and 2x1 minus x2 equal to 0, so this purple line here. Okay, so you can see that these two lines meet only at one point. Okay, so this system has a unique solution. Okay, similarly take another example, say one is x1 plus x2 is equal to 1. Okay, so one line this, and 2x1 plus 2x2 equals 2. So again this is the same line, so you can see that this second equation is just 2 times the first equation. If I multiply both sides of first equation by 2, we will get second equation. So they represent the same line in fact, and so they coincide at all the points on the line, and so there are infinitely many solutions for this system. Okay, and third case is when the two lines are parallel. So if I take the system of equations to be this, that x1 plus x2 is 1. Okay, so that's this red line here, and x1 plus x2 is equal to 2, so that's this line blue. So you see that these two lines are parallel and they will never meet. Okay, so this system of equations is inconsistent. There is no solution or no values of x1, x2 for which both the equations can be simultaneously satisfied. Okay, so for if solution exists, if there is consistency, then either we will have a unique solution or we will have like infinite many solutions, and if there is inconsistency, that means there will be no solution. Okay, so how we can check whether a system is consistent if you have a system of linear equations is we can utilize uh, this method. Okay, so if you are given a system of linear equations where you have given m equations in n unknowns, then we can rewrite this in matrix form as a times x is equal to b, where a is the coefficient matrix of the on the left hand side coefficients, where coefficients are a1 1, a1 2, a1n, a2 1, a2 2, so on a2n, and so on am1, am2 and amn. So This matrix is the coefficient matrix of the coefficients of unknown variables, which makes the matrix A. X is a column vector or column matrix with unknown numbers x1, x2, xn. Okay, so that their product is the left hand side of each equation, and B is the column matrix of the right hand side, b1, b2, bm. Okay, so I guess there are n, so it has to be bn here. Okay, not bm, this is bn. Okay, this is m. Okay, bm. Okay, here bm. Okay, so this is b1, b2, bm. So there are m rows, so it must also have m rows. Okay, so this is bm and not bn. Okay, so ax is equal to b, so this is b1, b2, bm. Okay, so this right hand side is the right hand side column matrix. X is the column matrix for the unknown variables, which are x1, x2, xn, and A matrix is the coefficient matrix for the left hand side coefficients. Okay, and we know how to solve this Ax is equal to b by writing the augmented matrix, and we know that augmented matrix K is by writing the two matrices A and B together inside a single matrix. So define the augmented matrix K as AB, and so if I write this matrix, so K we can write a inside a single matrix, this matrix A and this matrix B. So uh, there will be m rows and first n columns will be coefficients and the n plus 1 column will be the B column. So this matrix K will be m by n plus 1. Okay, so there will be m rows and n plus 1 columns to this. Okay, so if we write this matrix A, this augmented matrix K, which is combining two matrices A and B. So there will be first coefficient matrix A and the column matrix B written inside the single matrix. So there are m rows now and there are n plus 1 columns. Okay, and for consistency of this we can reduce it to equivalent form. Okay, we already know how to reduce a matrix to equivalent form. We have done that in previous lecture. So the system will be consistent. Okay, so the linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. Okay, so if we reduce it to equivalent form, we will know which of the columns are pivot columns. Okay, so when you apply row operations and find the leading elements and make all other elements zero below the leading elements, then the pivot positions and pivot columns will be formed, and the system will be consistent if this last column of this matrix is not a pivot column. Okay, or equivalently we can say that the linear system is consistent if and only if an equivalent form of the augmented matrix has no row of the form this 0 0 so on 0 is equal to b with b non-zero number. Okay, so if these two statements are same, because if you get a row of this form, then simply means that the leading element of this row is the last element, so that means this last column will be the pivot column. Okay, so both these statements are equivalent. Okay, the last column cannot be pivot column, and which is same as saying that there should be no row in this matrix after reducing it to equivalent form, which is of the form that all the first n elements are 0 in that row and the last element is non-zero. Okay, so 0 0 so 0 0 0 so on 0 and last element non-zero. That should not happen. If this happens, then the system is inconsistent. Okay, or last column becomes pivot column and we will not have any solution, because each row represents the this element is the right hand side of the equation and these elements are the left hand side of the equation. Okay, these are coefficients of x1, x2, so on xn. So if these are 0, then the left hand side of equation is 0 and right hand side becomes non-zero, so which is not possible, so system has to be inconsistent in that case. Okay, and so finally, if if you reduce it to equivalent form and the last column is not a pivot column, that means the system will be consistent then. Okay, and if the system is consistent, so it will either have a unique solution or infinite many solutions. And so when it will have unique solution, it will have unique solution when there are no free variables. Okay, so these are coefficients of variables. Okay, so and by saying free variable means variables associated with non-pivot columns. Okay, they are called free variables. Okay, so the system will have unique solution when there are no free variables. That means when there is no non-pivot column. That means all the columns are pivot columns. Okay, of a side. Okay, not on this side. This side has to be a non-pivot column and all other columns are pivot columns, then there will be a unique solution. And infinitely many solution when there is at least one free variable, that means there is at least one non-pivot column in the coefficient matrix A. Okay, so if you get any of the column of aij's, any one column as non-pivot column, that means there is at least one free variable associated to this, then there will be infinitely many solutions. Okay, so again just to add that this first column is these elements a11 a21 so on am1, they are coefficients of x1 in different equations. Okay, so this column is basically coefficient column for the coefficient of x1. Okay, so x1 variable is related to this column. Similarly, the second column is linked to x2 variable, third column will be linked to x3 variable, and so on. This nth column is linked to xn variable. Okay, and this is the right hand side of the equation, so these are bi's. Okay, so when we say there are no free variables means those x1 x2 so on xn, those variables or any of those variables should not be free. That means those variables are linked to some column, so that column should not be a non-pivot columns. Okay, so if all columns of A are pivot columns, then unique solution. If you get any one non-pivot column, okay, then there will be infinite many solutions to this system of equations. Okay, this same result was given in Rouche-Frobenius theorem, but here instead of talking about the equivalent form and talking about the pivot columns or non-pivot columns, they talked about the rank of the matrix. Okay, so in a sense they both are same. Okay, so let us see this definition first. The system of equations ax is equal to b is consistent if and only if the coefficient matrix A and the augmented matrix K are of same rank. Okay, so if the rank of the matrix A and the rank of the augmented matrix, which is AB, are same, if rank is same for these two, then we say system is consistent. Okay, now we know that rank of a matrix is the number of pivot columns. Okay, so if these two have the same rank, that means the pivot number of pivot columns in A and number of pivot columns in K are same. Okay, so which is same as saying that this B, only one column B is added to this matrix, that this B matrix, this B column is not a pivot column. Okay, so this definition is same as the previous definition, that the matrix, the system will be consistent if last column is not a pivot column. Okay, or equivalently we can say that these two matrices have the same rank. Okay, which is same as saying that this column is not a pivot column. Now addition to this, whether we can have a unique solution or infinite many solutions. So further in this theorem, that if rank of A equals rank of K, okay, that means last column is not pivot column, and it is equal to n, where n are the number of variables, then the system is consistent and have a unique solution. Okay, so consistent because these two ranks are equal, and unique solution because it is equal to n, and n are the number of variables. Now each column is linked to one variable, so if there are n variables, that means there are n columns. Okay, and if rank A equals n, this means that all the columns of the matrix A are pivot columns. Okay, so this definition is again similar to previous definition, which says that system is consistent with unique solution when there is no free variable. So this also says that there is no free variable because all columns of A are pivot columns. Okay, rank of A is n, means all columns are pivot columns for A. Okay, so there is no free variable. Okay, so this definition is again same. uh, the second part is that if rank of A equals rank of K, so that means system is consistent, there is no pivot position in B. Okay, and it is less than n, strict less than n, where n is number of variables, then system is consistent. Okay, because of these two are equal and have infinite number of solutions. Now this is again the same definition in the sense that if there are n columns but rank of A is less than n, means the pivot positions are less than n, so there is at least one free variable. Okay, or there is at least one column which is a non pivot column. Okay, and so it will have infinite number of solutions. And third case is very obvious: when rank of A is not equal to rank of K, then the system is inconsistent, and this only is possible when this last column becomes a pivot column in augmented matrix. Then in that case the rank of K will be 1 greater than rank of A, and so these rank will not be equal. Okay, so these Rouche-Frobenius theorem definition is same as the definition which we did on the previous slide. Okay, so now I take few examples here to show how we can check if the system is consistent or not. Okay, so in the first example there are four linear equations in four unknowns x1, x2, x3 and x4. Okay, so what we have to do is construct the uh, system of equations in matrix form Ax is equal to b. Okay, where x vector will be a column matrix with members x1, x2, x3, x4. B is the right hand side 5 0 3 0, and A is the coefficient matrix on the left hand side with first column as coefficients of x1, second column as coefficients of x2, third columns as coefficient of x3 and fourth column as a coefficients of x4. Okay, so we just write the system of equations. Ax is equal to b, where A is the coefficient matrix. Okay, so first row, this first column is the coefficient of x1, coefficient of x2, coefficient of x3, coefficient of x4. Okay, so in the first equation x1 coefficient is 1, x2 coefficient is -6, and x3, x4 are not there, so these values are 0 here. Okay, similarly from the second equation x1 coefficient is not there, so that value is 0, and the other 1 minus 4 1. Okay, in the third equation all variables are there, so we can easily write coefficients -1, 6, 1 and 5. And in the fourth equation again x1 is not there, so x1 coefficient is 0, x2 coefficient -1, x3 coefficient 5 and x4 coefficient 4. X is a vector which is x1, x2, x3, x4. Okay, so clearly first column is linked with x1, second column is linked with x2, third column is linked with x3 variable, and fourth column is linked with x4 variable. Okay, and right hand side is the these numbers 5 0 3 0. Okay, and because some of the numbers are non-zero, so this is a non-homogeneous system of linear equations. Okay, so now to solve this or to check whether the system is consistent or not, we just need to write the augmented matrix K and see how it behaves when we reduce it to equivalent form. Okay, so we'll row reduce the augmented matrix K, which is A matrix and B matrix written inside a single matrix, to check its consistency. So let us write K as 4 rows and 4 plus 1 5 columns. Okay, so if we write the augmented matrix will be this first 4 by 4 is a matrix, and this last column is the B matrix. Okay, and then we apply transformations to reduce it to equivalent form. Okay, so the first row, first non-zero element is there, so clearly this is our leading element, and we have to make every element below this 0. So the only transformation now we required is the row 3 element to be made 0. So row 3 plus row 1 and impact on row 3. Okay, so row 3 plus row 1 impact on row 3. Okay, so first, second and fourth row will not change. Okay, only the third row will change, and it will be changed by adding first row to third row. Okay, so 1 minus 1 0 here, 6 minus 6 0, 1 plus 0 is 1, 5 plus 0 is 5, and 3 plus 5 is 8. Okay, so 158 we get here. Now the second row leading element becomes this at 2 2 position, and everything below this we have to make 0, so we'll use row 4 plus row 2 impact on row 4. Okay, and by this element will become 0, minus 1 plus 1 is 0, this 0 plus 0 is already 0, so 2 zeros here. 5 minus 4 is 1, 4 plus 1 5, and 0 plus 0 0. Okay, so we get 150, and rest of the three equations are not changed because there is no transformation applied on first three rows. Again, now the third row leading element is 1 here, so we can make this element in fourth row third column, this bottom element 0, so we apply row 4 minus row 3 to make this element 0. Okay, so row 4 minus row 3 impact on row 4, and this makes 1 minus 1 0, 5 minus 5 0, and 0 minus 8 makes this last element minus 8. So in the fourth row this is the leading element, so we can see the leading elements, the pivot positions are this 1 1 2 2 3 3, and this fourth row fifth column. Okay, so first column, second column, third column, and fifth column are the pivot columns. Okay, so clearly you see that the last column is a pivot column here, or equivalently you see that there is a row of the form 0 0 0 0 and last element non-zero. Okay, so the system is inconsistent, there is no solution to this system. Okay, so augmented matrix has a row of the form this, so system is inconsistent. Okay, or clearly the rank of matrix A. Okay, so A is this 4 by 4. Okay, in this 4 by 4 there are 3 pivot positions, so rank of A is 3, and augmented matrix is this full matrix, and there are 4 pivot positions, so rank of K is 4, so rank of A is not equal to rank of K, hence system is inconsistent. So either way you can look at it. Okay, and you can say that this particular system is inconsistent. Let us take another example. Say examine the consistency of the system this. Now we have three equations in three unknowns x, y, and z. Okay, so we have to write it in matrix form. Ax is equal to b, and clearly you see that there is a number here on the left hand side not attached to any variable, so we must take this to the right hand side. Okay, so the first equation has to be written as 2x plus 6y is equal to minus 3, and then we will write the matrix. Okay, so the matrix equation Ax equal to b, where A is the coefficient matrix, where first column is column of x in each equation, second column is linked with y, and third column is linked with z, and b is the right hand side matrix. Okay, so this 3 goes to right hand side, so become minus 3 minus 3 3, this matrix B. Okay, and on the A matrix, the first row gives x coefficient 2, y coefficient 6, and z coefficient 0. Okay, so 2 6 0. Okay, x y z coefficients. Similarly 6 20 minus 6, and no coefficient of x, so 0 1 and minus 3. Okay, and now again we write the augmented matrix K, which is this A matrix, and last column as B matrix combination combined together in a single matrix, and then we apply elementary row transformation to reduce it to equivalent form. So this we have at 1 1 position we have the element non-zero, so it's a leading element. We use this to make this element R in row 2 as 0, so we apply row 2 minus 3 times row 1 impact on row 2. Okay, so row 2 minus 3 times row 1 impact on row 2, so this makes this element 0, and 20 minus 18, so 2 minus 6, and minus 3 plus 9, so it makes this element 6. Okay, again now in the second row this becomes the leading element, so we'll make this bottom element 0, so row 3 minus half of row 2. Okay, so row 3 minus half of row 2 impact on row 3, so if you divide this by 2 and subtract from third row and impact only on third row, so first two rows will not change. Okay, so 1 minus 1 0, minus 3 plus 3 0, and 3 minus 3 0. Okay, so every element in third row becomes 0. So clearly you see that there is no equation or there is no of these forms 0 0 and right hand side this last column non-zero. Okay, there are only two pivot positions and so two pivot columns, and so system is consistent here with the rank of A is 2. Okay, and rank of whole matrix also 2. Okay, system is consistent, and since third column is a free column or a non-pivot column, so this system will have infinite many solutions. Okay, so clearly rank of A equals rank of K, which is 2. Okay, 2 is the rank of A and 2 is the rank of K, but the total number of variables are 3. Okay, x, y and z. So clearly the system is consistent and have infinite many solutions. Okay, so I take one final example here, that for what values of h and k the following system is consistent. Now we are given this two equations in two unknowns x1 and x2, and h and k are unknown numbers. Okay, so what values or what numbers h and k can take so that this system is consistent? So again the method is same, that we write the augmented matrix from the system. Okay, so this can be written as x equal to b, where a is the coefficient matrix, so 2 minus 1 minus 6 3 is the a matrix. X is a matrix of unknowns x1 and x2, and right hand side is hk, b is hk column matrix. Okay, and we write the augmented matrix a and b. Okay, and then apply transformation to reduce it to echelon form. So we, this is the leading element, so we make this element at 2 1 position, minus 6 to 0, so we have to apply row 2 plus 3 times row 1. Okay, so row 2 plus 3 times row 1 impact on row 2, so this element becomes 0. So again 3 minus 3, so this also becomes 0, and k plus 3 times h, so this becomes k plus 3 times h. So now it is equivalent form. Okay, and if this k plus 3h, if it is a non-zero number, then the last column becomes a pivot column and system will be inconsistent. Okay, and so for consistency this element also has to be 0 because all the other elements are 0. Okay, so system will be consistent if k plus 3h is 0 or k is minus equals minus of 3h. Okay, so if k equals minus of 3h, then the system is consistent and have infinite solutions, because the second column is always a free column. Okay, there is only one pivot position. Okay, in the first column, second column do not have any pivot position, so it's a free column and there will be always infinite solution if the system is consistent. And if k is not equal to minus 3h, then system is always inconsistent. Okay, so this is how we can check the consistency of system of equations. Okay, and now we close this topic for today here, and in the next lecture we'll talk about vectors, and then we will give you a bit of interpretation that how the solutions of the system of linear equation will be represented in whether it is in R2 or R3, and then we'll again talk about the system of homogeneous equations and system of non-homogeneous equations and their solutions. Okay, till then have a very nice day.